Hello, my name is Ben Williams. This is my Lab 6 presentation for Physics 2212. The introduction to this lab, the purpose is to drop a magnet through a non-magnetic tube of aluminum to see how the flux changes over time and to see how that changing flux induces a magnetic field and how the changing flux creates a force on the falling magnet that opposes gravity. The principles of this lab are the dipole fields of magnets and magnetic flux and Faraday's law. What we found is the magnet takes about 1.1 seconds to fall through the tube, which is longer than it would take if it was only being acted on by gravity. And the field strength drops off with distance cubed. These are my experimental findings. So here's the video of the lab. See that the second 1.1 seconds drop through. The magnitude of the magnetic dipole is 0.1814, and that's from the previous lab. The mass of the magnet is 0.0223 kilograms, and the length of the tube is 0.27 meters. The computational model we used assumes a couple of things. It assumes that the cylinder is a perfect cylinder. It assumes that there's no air resistance on the magnet and assumes uniform resistance and current throughout the tube. This is the computational model. So it found that the magnet was in the tube for 0.803 seconds. When in the middle of the tube, very little change in flux, so constant velocity. So you can see as this velocity versus time graph, and initially is going quite fast, and then it slows down before finding a very constant velocity. This is when it's in the middle of the tube, and then when it reaches the end, it drops off again. This is the code for the lab. It loops through every ring in the tube. It sets up the tube as a stack of many, many rings on top of each other. And it finds the flux through each ring created by the bar magnet. And then it finds the current through each ring by dividing the flux by the resistance on the ring. We can then use that information to find the B field at the ring, and we can use that information to find the magnetic force on the ring. And then we can use the magnetic force on the ring to add that to magnetic force on the magnet, because that's by Newton's first law, or Newton's third law. Sorry, each force has an equal and opposite reaction. This is the method we use to calculate the changing flux on the magnet. The magnet creates on each ring. You can see that it takes into account the radius, the position, and then this long complicated formula which was given to us. So our measured versus computed values, the measured time was a little bit longer at 1.1 seconds in the tube. The computed time was 0.083 or 0.803. That's for a couple of reasons. There are a few sources of error in this lab. Notably, the measured values of the magnet were likely wrong, as the magnetic dipole moment was not an accurate measurement. That was from our previous lab. It was just a mistake. The resistance of the tube also could have been off. The given value may not be what the resistance of the aluminum actually was. And additionally, the actual geometry of the tube we used was not a perfect circle on the inside, so that the cylinder we modeled it as is not perfect. So what if the resistivity of the conductor were reduced close to zero? The induced current would be much higher, so the force of the magnet opposing the falling magnet would be stronger, so the magnet would fall slower. If there were holes cut into the tube, there would be less rings, so there would be less induced current, and thus the magnet would fall faster. So in conclusion, induced magnetic field opposes changing flux, thus opposing gravity on the magnet. Thank you.